Let's try an example of finding a derivative for a composition of functions involving a multivariable function. So the problem I have written here on the screen came straight out of the textbook. I'm not a big fan of the way that it's laid out because it's a little bit overwhelming. So let's break it down. I see z depends on a function f depends on x and y, where x and y are each functions of t. So I can see that we have variables z, x, y, and t. Z is going to be dependent, x and y are going to be intermediate, and then t is independent. Let's go ahead and make our flowchart involving all four of these variables. In the flowchart, the independent variable is always at the bottom. It's sent up to the intermediate variables. So we know that t goes into the function sine t to create x, t goes into the function cosine t to create y. Together, x and y are bundled up as an ordered pair. They are sent into the function f to create z. So we can see our flowchart here. This is helpful with creating the partial derivative. Sorry, not the partial derivative. For creating the formula that we're going to use for the chain rule. So we are asked for dz dt. dz dt is the total derivative we're looking for. But we have to pay attention to the fact that z doesn't go straight to t. It's going to pass through some intermediate variables, like x and y, and then x and y make their way to t. So we're going to have two terms, one where z is going through x first, then t. So we'll need the partial of z with respect to x times dx dt, plus the partial of z with respect to y times dy dt. And if you're not sure about why we're writing this way, go back and watch the first video from the section. It'll help break down this flowchart. Now that we know all of the different factors that we need for the calculation that we're doing, let's write them out and do a little bit of scratch work. So we need the partial of z with respect to x. We need the partial of z with respect to y. We also need dx dt, and we need dy dt. Let's go through and do our partial derivatives. So to take the partial of z with respect to x, we're going to look at the definition of z, which is right here. Taking the partial of 4x squared, that would give us 8x. Taking the partial of 3y squared with respect to x, that's just a 0. Looking at that same definition z, but taking the partial with respect to y, the partial of 4x squared with respect to y is 0, plus the partial of 3y squared with respect to y, that becomes 6y. Then we need the derivatives of x and y, each with respect to t. So looking at the definition for x, a function of t, that's just sine t. If we take the derivative of sine t with respect to t, we get cosine t. And then when we do the derivative for the y function with respect to t, we see that y as a function of t is cosine t. So taking the derivative of y with respect to t, we get negative sine t. Now that we have all four of the pieces we need, we can plug them into our chain rule formula. Starting with that first term, partial z with respect to x, that came out to be 8x, times dx dt, that's cosine t. Next, we add the second term, partial z with respect to y, that looks like 6y, times dy dt, which was negative sine t. we can clean that up a little bit, right? 8x cosine t minus 6y sine t. Now, listen up. Lots of us are going to stop right here, but be careful, you probably shouldn't. The question is asking about dz dt. How does z change with respect to t? And we're answering that question with an expression that involves x, y, and t, and that's a little bit too much. We want to replace x and y with their definitions depending on t. So instead of x, we should write sine t. The t's can stay the same, they're fine. But x and y need to be replaced with their version of functions of t. So our final answer, dz dt, will have 8 sine t cosine t minus 6 cosine t sine t. And now that we've replaced x and y with their functions of t, we can see that this simplifies even further. 8 sine t cosine t minus 6 cosine t sine t. Well, if we just rewrite one of these terms to match the other, we can see that they're actually like terms. If we start off with 8 of them, subtract away 6, we're left with 2 of the sine t cosine t products. So this would be our final answer. Z changes with respect to t the way the function 2 times sine t times cosine t changes with respect to t. Now, admittedly, this is a pretty simple example of using the chain rule for a multivariable function. Notice that each of the functions we worked with, f, x, and y, they were all fairly simple. And of course, that's just because we're trying to illustrate how this process works. In the future, we'll work with more complicated functions where you really need to do it this way. Lots of us are going to be tempted to create the composition of functions by substituting in. For example, you could, instead of writing z equals f of x, y separately, we could rewrite this as z equals f of sine t cosine t. And then that function is going to look like 4 sine squared t plus 3 cosine squared t. Notice that with this substitution, z becomes a function purely of t. And when we do our derivative this way, it might feel like it's a simpler process. Please excuse my dog. She can't control herself. Shh, lady, you're being rude. What I was saying is, if you do this substitution where you replace x with its definition and cosine for y, you will create a function of only t. This does not require the chain rule, not in the sense of using a multivariable function with intermediate variables. This looks a lot more like a Calc 1 problem, where z is a function of one variable t. In fact, if you were to find dz dt using this function that we have, you'll get the same answer that we got. And so for some of us, it might feel like that's the faster way to do this problem. And I get it, but that's only because this example is using very simple functions. We're not using anything crazy here. So practice using the chain rule. Check your work using this substitution and Calc 1 derivative process, but make sure that you know how to do it both ways. Don't just do the substitution and Calc 1 method. Make sure that you're learning this new chain rule as well. All right, next example. Here we're asked to calculate dz dt, where again z is a function of x and y, x is a function of t, and y is a function of t. I'm going to go ahead and write out all of my work for this problem, so pause the video now, give it a try on your own, and then compare your answers. Alright, so I've worked out this problem myself and written my work here on the slide for you to compare to.